We have the great pleasure to have Professor S. Pushpavanam amongst us as the guest of honor as well as the speaker for today's institute lecture. And lecture demands that I introduce him to the benefit of our students who know him. He is graduate from University of Florida with a PhD in chemical engineering. Thereafter, he secured a faculty position at IIT Kanpur, but made a transition to IIT Madras, where he is currently the YPG Warma Chair Professor in the Department of Chemical Engineering. His research is primarily in the area of advanced transport phenomena, which deals with multi-phase flows at microscale level, also known as microfluidics. The motive behind this research work in microfluidics is to revolutionize the chemical industry and diagnostics. As an outcome of the research work, he has co-authored over 130 plus publications and has written 2 books, namely Mathematical Methods in Chemical Engineering and Introduction to Chemical Engineering. Notably, his book on mathematical methods in chemical engineering is used in several IITs and other academic institutes to develop a course in mathematics. He has played a pivotal role in providing research guidance to several undergraduate, MTech, and PhD students. In addition, he is also known worldwide for his NPTEL lectures on multi-phase flows, analytical solutions, and stability analysis. Furthermore, he has received various prestigious awards like the Fulbright Fellowship, Rajan Prabhu National Award, Professor YGB Verma Award for Excellence in Teaching, Discovery Award to Incubate a Startup in United Kingdom, and Grand Challenges Exploration India Award by the Bill and Melinda Foundation. With this introduction, I request Professor Pushpavanam to come to the stage and address us on the topic that he has chosen for today's lecture, Microfluidics, Revolutionizing Chemical Industry and Diagnostics. Professor Pushpavanam.
Good evening, and gives me great pleasure to be here today. And I was in this room about 6 years ago giving a talk, and just feels nice to be back here. I think that event, Chemical Engineering Department was celebrating some event on that day. 5:30 in the evening is a difficult time for a seminar, but I'm glad that all of you have taken the effort to come to the talk. This is going to be a live talk. Before I get into the topic, I just want to mention that I thank the organizers for the invitation. I think it's a great pleasure for me to be here because I think this is a very prestigious institution where noble, great people like Pandit Madan Mohan Malviyaji, fondly known as Mahamana, was the chief architect behind the foundation of this university, and gives me a very nice feeling that I am on a campus which was actually built by such great thinkers, great visionary leaders. And I would strongly encourage that all the students who are here to basically take some time and spend some time reading about Pandit Madan Mohan Malviyaji, because I think to set up this kind of a university those days, he had to undergo a lot of challenges, and the way he overcame those challenges is a story, as an inspiration in itself. And I think we can learn a lot. Today we also face challenges of different kinds, and reading about him would definitely be a good way to address challenges that we may face in our lives. So you should capitalize on the rich heritage of this institution, and I'm very happy that I'm here today, and this proud heritage that you all are going to be a part of when you graduate as alumni. Okay. So with that, I would like to start the discussion. This topic is basically microfluidics, and I'm going to give this as a very general, broad talk, not getting too much into the scientific details, just to give you an idea of how to go about thinking about a problem. Okay, most of us are very engrossed in the details. And as a researcher doing a particular research, you have to worry about the details. But you need to have a broader perspective as well. So what I want to do today is try to paint this broad perspective so that you can take lessons from this broad perspective and possibly use it in your area of research, whatever it is. It could be in a different area. Okay. So that's how I've planned the talk, so that it's not necessarily going to be actually, something only for people working in microfluidics, but it's basically catering to a broader audience. So, sometime back when I was a undergraduate student at IIT Madras, most of the computational work used to be done in these mainframe computers. So this is an example of a mainframe computer, an IBM mainframe computer, and you can see the size of this computer. I mean, it used to be possibly occupy something as big as this room. And we used to write our computer codes in a language called Fortran. That was the language which was the language for scientific purposes. Okay, and we used to have punch cards, and we used to have to punch those cards in, and then we would run it on these mainframe computers. And those were I'm talking about the 1980s. Today, if you look at it, the same computational power that was there in these big mainframe computers, you possibly have in these laptop devices. Okay, most of you have laptops, and the computational power in these laptops is maybe even more superior to what was present in the mainframe computers. So basically, what has happened in the electronics industry is we've been able to shrink these computers from the size which was occupying an area volume as big as this room to something on the laptop. Okay, and what has actually made this happen is because we've been able to pack more and more transistors into our integrated circuits. Okay, and so more functionality was built in these devices. Okay? And there's something called the Moore's law, which talks about how the number of transistors which are packed into the integrated circuit doubles every 2 years. This is more of an empirical relationship which basically came up after the looking at the data about the technological advances. This is not a fundamental law like conservation of mass. It's an empirical relationship. Okay, so looking at the data of how the size of the transistors, how the size of the IC was shrinking, this law was coined. In fact, he was one of the founders of IBM. He passed away recently. The question we want to ask is, if you look at a chemical factory, think of a chemical factory. Normally, the image that you have is of these big factories, right? And that's an image you have of these big factories. And the common thinking was that you need to have these large factories because of the economics. The economics of scale has to be exploited to make production of any chemical profitable. So unless you did this at a large scale, you could not really have a profitable chemical industry. That was the thinking, and that's how chemical industry grew in the good old days. The question which you are asking is it possible to do something revolutionizing as it is for the electronics industry in the chemical process industries, and can we shrink the functionality of what is done in a chemical plant into a smaller device, in a smaller unit, like maybe make a chemical plant which you can carry in a briefcase. Okay, so we are talking about shrinking, looking at what happened in the electronics industry and trying to translate that into the chemical process industry. And of course, the translation is not going to be direct and straightforward. So we have to look at what exactly are the differences, what are the similarities. So the motivation for doing microfluidics basically came from that. Okay, is it possible to shrink things so that you can possibly get all the functionalities of a chemical plant in a small device which can do the reaction, which can do the separation, etc., etc. Okay. So, what are the basic? What this slide talks about is when you talk about miniaturization in the semiconductor industry, you are talking about flow of electrons. Okay, and electrons move at the speed of light. Now, what we are doing in the chemical plant is you are talking about flow of fluids, right? Liquids are being pumped, gases are being pumped, okay? And so there is a very finite velocity with which these fluids are going to flow. So that's one difference you have, okay? And then you have, because you are talking about reducing the size, the viscosity of the liquid, the viscous resistance which the fluid gives to flow becomes a very dominating factor. So that's something which you need to worry about. The other important thing is, as you start shrinking the size, the surface tension effects become more important, because compared to volumetric effects, the surface effects become more important. So surface tension has to be included in the design, and it can have a negative effect, it can have a positive effect. So when you talk about bulk reactor, the volumetric effects are important, surface tension effects are not all that important. So that's a major difference when you shrink the size of a chemical plant. When you go from a large plant to a small plant, viscous effects and surface tension effects have to be factored in. And so this is basically what we have. The advantage of doing the operation is that your flow in a microchannel or a millichannel is going to be very well defined. That is, you don't have turbulence, for example. Okay, you don't have turbulent flows that you would possibly have in a large-scale reactor. And so that is an advantage, but there is also a disadvantage which comes. And the disadvantage which comes is because of the flow being laminar, you may have issues with mixing. So if you have a big reactor, in chemical reactions, you want two molecules to react. You want to have good contact between the two molecules. In a big reactor, you can put a stirrer and you can mix things up. Whereas in a small vessel, you may not be able to do that. Okay, so so that's a challenge. So this is basically an example I have of millichannel on the top, where because of the flow being well defined, the flow is what we call laminar. All the streamlines are parallel, and the velocity profile is parabolic. Okay, as opposed to what you see at the bottom, which is a turbulent flow, where there's good mixing in the radial direction. So the question was, you can shrink the size, but how do you improve mixing? Okay, so because if you want to do a chemical process in a small scale, you want to improve mixing. And one thing which can help us do this is realize that when your channel is not straight, it is bent, as you see here, is bent because of the curvature. Okay, there are centrifugal forces which come into the picture, and these centrifugal forces are going to basically generate what are called vortices along the cross section. Okay, and that's basically what you see here in the bottom. You see vortices which are generated, and these are generated because of the geometry of the channel. The geometry of the channel, which is curved, has centrifugal forces, so the liquids are thrown out, and because of continuity, they keep circulating. And because they circulate, we get mixing. So a simple change in the geometry can help us get mixing. Okay, and this is where the fundamentals of fluid mechanics, whatever we teach in the class, the teachers are teaching you in the class, they can be used to solve a problem called mixing, and these are basically called these vortices. Okay, other issue is the reaction rates are usually very slow, and sometimes if you want to carry out a reaction in a reactor, you have to wait for a very long time, which means your velocity is very low. The length of your reactor or millifluidic device or microfluidic device has to be very large so that it can spend that much time in the reactor. So, but the whole idea was to make it more compact. So one way to basically get a compact device with good mixing is what I'm trying to show you here. Okay, you see here basically a reactor which is coiled around, okay, a rectangle, and what the coiling does is it gives you first of all deep vortices which help you in the mixing, and secondly what it does is it also makes it more compact. So a big long length has been really compressed into a very small area, small volume. So now you basically have the advantage of having a compact device which can also have good mixing. Okay, so this is basically what we have, what I'm trying to show you here, and these are pictures of the vortices which help you mixing. I will not bore you into the details of how mixing is better because of this geometry, but that's getting into the details. Okay. Yeah. So I want to basically, so that part was about the fundamentals, and we wanted to see if we can actually do some synthesis of nanomaterials, nanoparticles in these kind of microfluidic reactors, okay, and exploit the well-defined flow fields that exist in these microfluidic reactors. Okay. So this is just a general slide which talks about nanoparticles and what are their advantages. So if you have a bulk material, okay, there are some properties which you have, but when you really take nanoparticles of the same material, it could be silver or gold, there are lots of nice properties which are basically exhibited. Okay, for example, they could be catalytic, they could be antibacterial, and they could be having some nice optical properties like exhibiting LSPR, surface plasma resonance. So that's the kind of properties that you can have. So that is basically a strong motivation to make nanoparticles. One of the challenges which arises when you make nanoparticles is that you want to get a uniform size particles. Okay, you don't want a particle size distribution. So how does one overcome this problem of getting a very large particle size distribution and come up with a narrow particle size distribution? So that's the thing, and because when you do it in a large scale reactor, there are some portions of the reactor where the mixing will be good, some portions where the mixing will be poor, and so there is going to be non-homogeneity in the product that you're going to get. Okay, so is it possible to use these kind of microfluidic reactors to actually get the better quality product, which could be nanoparticles? And I will just go ahead. So the idea, one of the things that people have done, researchers have done, is use the two-phase flows. That is, you can have an organic phase and an aqueous phase flowing. So what I'm trying to show you in this picture on the right, just focus on the picture. There are two different fluids. You have organic phase and an aqueous phase, and one possible flow regime is this kind of a sludge flow. That is, you have a dispersed phase. You have a dispersed phase which is in the form of these ellipses that I'm showing, and it is flowing along with a continuous phase which is transparent. Again, the fluid mechanics tells you that because of the shear forces which are acting on the interface, you will have internal circulations in the dispersed phase. Okay, so since we are mainly chemical engineers here, each of these drops, each of these slugs can be thought of as a reactor, as a well-mixed reactor. And you can see that because of the well-defined flow conditions, you are able to get uniform sized drops. The size of the drops is uniform, you get uniform mixing. And so the general thinking was that you can you'll get better quality product. Okay, this was the motivation for doing this kind of a two-phase synthesis. So you will see a lot of areas, a lot of applications in what is called droplet microfluidics, where you basically have a dispersed phase and a continuous phase. There are a lot of applications. I'm just talking about one application here, which is the nanoparticle synthesis. Now, the advantage here, of course, is we are in a position to do the synthesis in a continuous manner. Okay, so normally you can pump and we can continuously get our products. Now, but however, there is a small disadvantage in this. The disadvantage of what you would do is you would possibly put the reactants, the two fluids, okay, in the organic phase and the aqueous phase, and then the reactants have to come from the aqueous phase, from the continuous phase to the dispersed phase through some mass transfer, and then there has to be mixing. But that's how the whole thing works. But what we are going to do is, so the bottom picture, what you see is basically some simulations which we've done for the organic and aqueous two-phase flow in a dispersed phase, okay, with a discontinuous phase. Okay, so now basically what I'm trying to show here is that you can do experiments and try to understand what these flow patterns are inside the drop. You can also do simulations and understand the flow inside the drop. Now, there is the earlier slide I spoke about getting two phases. One is an organic phase and the other is an aqueous phase. But when you make your particles, make your material using that kind of a system, there is a small disadvantage. The disadvantage is that the nanoparticles which are synthesized cannot be used for biological applications, okay, because you are using an organic phase. So that is something which is a big drawback. You can make your beautiful nanoparticles, but you cannot apply it for a biofield, in a biological application, maybe for drug delivery or whatever it is. So how can you overcome this problem? Okay, and this is where the thermodynamics helps us, because there is this system called the aqueous two-phase system. So we have two phases now. And both the phases are aqueous. Now, and there are a wide variety of aqueous two-phase systems. But usually what will happen is in one of the aqueous phases, we'll be having a polymer like polyethylene glycol, and the other phase will have a salt, it could be citrate. Okay. So there is this literature about ATPs which exists. It says, look, so now we don't have any organic phase. And there is a lot of aqueous two-phase systems in the literature. Now these salts and polymers, they act as reducing agents to silver ions. So what happens is they can reduce the silver ion to silver nanoparticle or gold ion to gold nanoparticle, and you can get your reaction done, okay, in a without any organic phase, and that basically solves the problem. So here, what I'm trying to show you here is that the flow, when you have two aqueous phases, in an aqueous two-phase system, the two phases, when they flow, they are going to flow what is called a parallel flow. They're going to flow side by side. It's not easy to get the sludge flow, the one where you had the drops present in a dispersed phase, which I showed you earlier. The reason for that is again fundamentals. The surface tension of these systems is very, very low. Okay, so my point is, whenever you are doing something, you have to go back to your fundamentals and understand things. You need to have a clear understanding of fundamentals to overcome challenges. The surface tension of these aqueous two-phase systems is very low, and so if you really want to get a dispersed phase flow, a slug phase flow, you need to go to a very, very, very low flow rates. If you go to a very, very low flow rate, your productivity and all that becomes very small, very bad. So one doesn't want to go to a very low flow rate. So is there a solution to this problem? Okay, is there a way by which I can get a droplet flow, a dispersed phase flow in an aqueous two-phase system without going down to a very low flow rate? Okay, that's the question you are asking. And the idea is you go to okay, you realize that you should go, you should possibly have a flow with what is called, by modifying the capillary number, which will make sure that the inertial effects are less dominant and surface tension effects are going to be more dominant. Okay, surface tension is the one which is going to give you the drop. So in order to get a drop, if you want to make the surface tension effect more dominant, one way to do it is to go from a microfluidic system to a millifluidic system. But what is a microfluidic system? When your characteristic dimension is about less than 1 millimeter. Okay, you're talking about 500 microns. The diameter of your pipe is about 500 microns, 100 microns, 200 microns. But if you decide that you can live with pipe of dimension, 1.5 millimeters, 1000 microns, 1500 microns, automatically the surface tension effects become more dominant. So again, this concept of dimensionless numbers, which talks about relative effects of surface tension forces to viscous forces to inertial forces, is something which we can exploit. And then we can modify this and say, look, we're going to do this in a millifluidic system. Okay? And so that's what we did. We said we'll overcome this problem of using these microchannels which were not solving our problem by going to a millifluidic system. There is no compromise on the quality because the flow rates are still well defined. The flow regimes are well defined. They are very uniform. Okay, you have good dispersed phase flow, uniform size drops. So there's no reason why you have to worry about any quality of the product being bad. And what we also found was that when you make these nanoparticles, the silver nanoparticles or gold nanoparticles, they have a tendency to spontaneously come to the interface and get trapped there. So normally when you make nanoparticles, they are going to be in the bulk solution. Okay, and separating out these nanoparticles from the bulk solution becomes a challenge. So what I'm trying to show you on the right is that you have these two phases, and these nanoparticles which are synthesized using this aqueous two-phase system, they are actually going to be trapped at the interface. So your bulk solutions are basically free. You can harvest the solution from the interface and you can get your product nanoparticles. So by going to this kind of millifluidic system, okay, where I am able to get dispersed flow for a low surface tension problem system, okay, I am able to get good quality of the product and also able to simultaneously synthesize and separate the product. So that's an advantage. Okay. So this business of separating, of course, then what you do is you start thinking about what is it that makes this trapping at the interface happen. So you need to start thinking about what makes it happen. You have to understand the thermodynamics, the forces, and then get a more general perspective, because experimentally we have shown it. Then we have to understand theory, fundamentals to find out whether this kind of a phenomena is going to be universal. Is it going to happen for all nanoparticles, or is it going to happen only for some nanoparticles? So experiments give you some insight, modeling and simulation, understanding your forces give you another insight, and then you put all of this together to develop new things. One of the questions which people have is that when you do microfluidics or millifluidics, the volumes you are processing are very small. So how are you going to get large throughput? So the answer to that is we do the whole increase of throughput by having a lot of these millifluidic reactors, microfluidic reactors in parallel. Okay, and that's basically what I'm trying to show here. We have, we have a lot of these reactors in parallel, and basically the advantage here is that the entire system now becomes modular. So if you have one particular reactor which is not functioning properly, and what you can do is you can throw out that particular reactor, all the rest of the system is going to be working fine, and you can replace that module. So you don't have to really take a shutdown of the plant just because there is a malfunction in one particular module. Okay, so the way you do the improvement in throughput is by what is called numbering up. Okay, and that's basically what I'm trying to show you here. Numbering up is the way to go about doing these throughputs. Okay, so I'm going to slightly shift gears now. I'm going to talk about paper-based microfluidic devices. Why do we need paper-based microfluidic devices? It's because in all these other applications that you saw earlier, you needed a pump, a syringe pump, to pump the two fluids. Okay, and if you're trying to talk about making some sensors or making some device which you can take to the field in and monitor the presence of heavy metals, monitor the presence of some chemicals present in, let us say, some remote lake in a village, you normally would take the sample, bring it to a lab and do the testing. So the question is, can I make a sensor, can I make a device where I can directly go to the field, on the spot do the testing, get my result? Okay? And you don't want to carry too many of your things, accessories like pumps, etc. with you, because you may not even have electricity the place where you're going. Okay? So the idea is we are going to talk about microfluidic paper-based devices, where because of capillary action, because papers are inherently porous, okay, they are very fine pores, and if you drop some liquid, the liquid is going to basically spread because of wicking, okay, because of capillary action. And so you are having spreading of the liquid without necessarily, the fluid is going to flow on the paper without necessarily needing a pump. Okay, so is that something which we can exploit, okay, for making a sensor? That's the question. So I'm just giving you examples of two paper-based device sensors which are commonly seen. One is the glucose meter, okay, which if you have diabetes, you have these devices at home where you can do your own testing rather than you go to the lab and do the testing, okay, and you can monitor your glucose levels. And the other is the pregnancy strip for testing. So these are two things which are very common, which have been used, okay, and so the question is, can I basically extend this to monitor pollutants in the atmosphere, in water bodies, or for other things, okay, for healthcare purposes, for example, okay. So that's the idea, that's the motivation. So I'm just trying to bring you the motivation of capillary flows on paper, where I don't need to have pumps, it's going to flow spontaneously, and I can possibly think in terms of an application. So what this slide basically tells you is some advantages of having a paper-based device. Okay, things like you need very low volumes of chemicals, maybe microliters of chemicals for doing the analysis. You need it's portable. You can take it, carry it with you, for example. Okay, and I'm not going to read out from here, but is reasonably fast. So there are lots of advantages of having these kinds of devices. Okay, and you also have applications, environmental monitoring, healthcare, etc. on the right hand side, agricultural quality products, the quality of the agricultural produce if you want to mention. So I'm going to basically talk a little bit about these things to give an idea about how to think about a problem. So sometimes you understand a problem exists and then you try to see how you can use whatever chemical engineering principles are there to address a problem. Okay? So right hand side you see different applications, left hand side you see advantages of paper-based microfluidics. What we want to do when you talk about capillary flow on a paper is you want to make sure that the flow is going to be uniform in a particular direction. You don't want the flow of the liquid to be random. Okay, you don't want the flow of the liquid to be in any which direction it wants to go. So how do you make sure that the flow of the liquid is going to be in a particular direction, in a particular place, so that you can carry out your analysis? Okay, so that's basically the important thing. You have to therefore make certain portions of the paper hydrophobic, which means it hates water, and certain portions of the paper hydrophilic, which likes water. So make some portions hydrophobic, so water cannot penetrate that. Make some portions hydrophilic, so water will penetrate that. Okay, so if you can make a pattern on a paper where you have hydrophobic and hydrophilic, the liquid is going to flow only through the hydrophilic portions where it likes water. Okay, so you can get directionality to the flow by making the paper, by patterning it with hydrophobic and hydrophilic regions, and that's basically what we are trying to do. Okay, so the paper-based analytical devices basically need some portions where liquid will flow, some portions where liquid will not flow. And the World Health Organization has this criterion called the assured criterion. Okay, and the thing is, this is the acronym for assured. It has to be affordable, it has to be cheap. The other thing is, it has to be sensitive. Sensitive means you should be able to detect very, very low concentrations, because most of the pollutants that are going to be present are going to be in very, very low concentrations. So you have to make sure your sensor can detect such a low concentration. Okay? If you don't have good sensitivity, then you will have this problem of false negatives. That is, what is the meaning of false negatives? It will say the sample is not, the liquid does not contain your chromium heavy metal, but it will actually be present. That's a false negative, because you can detect only ppm, but what is present is ppb, parts per billion. But your sensor can detect only large concentrations. The other thing is, it has to be selective. So, what is the meaning of or specific? Your sensor should detect only your particular analyte, your chromium or your arsenic. So, arsenic may not be there, but if your sensor detects something else and gives you a signal, then you have a problem. Okay, so these are basically some criteria which we have to keep in mind when we try to design sensors. I'm not going to go through all of this, but it's basically called the assured criterion from WHO. So one thing which we have done in our lab is PRL. My students say they belong to PRL, push research lead, is how we can use a common laser printer, commercial laser printer, to make these paper-based devices, fluid devices. Okay, so I want to caution you, you can't use any laser printer because the toner ink varies from printer to printer. Okay, so the composition of the toner ink is very important. So there's a particular laser printer, the details are there in the manuscript, where you would have some amount of wax present in the toner ink. Okay, you print out the particular design that you want. So on the top, you see that you have this, the black region are basically the hydrophobic regions. Liquid cannot penetrate. The white region with the 3 amps, that is the region where the liquid can flow. So if I want to put the liquid somewhere here at the lower end, the liquid is going to go up by Capillary reaction and then spread into the 3 arms. The 3 arms, I would possibly have some chemicals preloaded. Because of reaction, I will be able to sense what is happening. So the reaction usually will be accompanied by some chemical change, some color change. Okay, so that's the basic idea that we have. And what we do is this mild heat treatment step to make sure that the wax penetrates the thickness of the paper so that we have hydrophobic walls, and then that the flow is going to be unidirectional. Okay, so that's the basic idea. So again, we tried this. We got this paper, but then we had a problem of the liquid penetrating from below. This heat treatment made sure that the wax penetrated the thickness of the paper, and we had nice walls through which the liquid could flow. Okay, so again, some details are there, but you need to, when you're trying to solve a problem, you will see that there are some challenges which come, and then you know how to think about how to overcome those challenges and then move on. Okay, I'm just trying to give you a broad idea about what the thought process was and what the challenges were and how we overcame it. So I'm just now the next few minutes. Okay, I have time. So I am going to possibly talk about a few applications. Okay, in the next few minutes of how we can use these paper-based microfluidic sensors. I'm going to talk about again the principle behind which these sensors are working. Okay. Most of this is published, okay, and you can definitely look at the manuscripts for more details. So one particular pollutant which is something which we need to worry about is the nitrite, NO2 minus ion concentration. And this particular sensor is working on the principle of a chemical reaction. It uses the chemical reaction, and because of the chemical reaction, there's a color change. So it's a colorimetric sensor. Okay, so there's a color change which is there, and I try to give you the reaction at the bottom. So you have the reagent which reacts with nitrite, it forms a complex, this gives you a color. Okay, and this color has a particular peak at a wavelength of 520 nanometers. So you need to understand that the principle of the sensor is based any colorimetric sensor. If you're trying to detect a particular analyte, like nitrite in this case, you have to look for some agent which will react with this nitrite and give you a color change. So, and you detect the color, the intensity of the color is going to be proportional to the concentration of nitrite. So the more the nitrite, the more intense will be the color, and then you get a calibration by looking at the concentration of the intensity of the color. You will be able to know what is the concentration of the nitrite. So that's how it works. Okay, so that's the idea. So the chemical reaction which induces color, and you can make this kind of a microfluidic device. You can pour nitrite of different concentrations at the dumbbells on the far side. Towards the center, add the reagent, it's going to react, you get different color intensities, and you can get your calibration graph. So that's one way to get an idea of what is the sensor working on. Okay. The next example is for a paper-based device which is going to detect the presence of E. coli. And again, this is basically the area of biotechnology. And the way I look at it, chemical engineers are so interdisciplinary. They can migrate into any area. Okay, biotechnology is something which we can easily absorb. So, for example, here what is happening is E. coli is going to take lactose as a substrate and is going to release these other glucose molecules. And in the process, there is also an enzyme, beta galactosidase, which is released. This enzyme is inside the cell of the bacteria. So you need to lyse the bacteria, you break open the bacteria so that this enzyme comes out. When this enzyme comes out, you would again have this color change reaction film showing at the bottom. Okay, so you have this CPRT being reacted with this enzyme, and you get CPR. So you get this color change, and this color change basically is going to tell you whether you have E. coli or not, and what is the concentration of the E. coli present, the bacteria present. So this is again an example. So again, strong fundamentals in biotechnology, okay, are important. And whatever the basic idea of colorimetric change, whether we can combine them and develop a sensor. Yeah, so this is basically something tells you how with the concentration of E. coli, the color is changing, and you can get your calibration color. So you can find out how much bacteria is present in a water solution by looking at this color change. So in some sense, if you look at it, you have seen pH strips that you use in a chemistry lab. Okay, there's a color change. Depending on that, you decide what the pH of the solution is. What we are doing is we are generalizing that idea to, I would say, more specific applications, more advanced applications. Okay, and of course there are challenges. I'll talk a little bit about it towards the end. Right now. So most of the work which people have done in the past, they have worked with making these sensors in liquid solution itself. So you have to go from sensor to a paper-based. Okay? So you need to go from a homogeneous liquid phase system to a paper-based with a heterogeneous system. And you need to therefore do a lot of optimization. And that is a challenge which we have. Okay? When it comes to translating a lab test which is done in a liquid phase to a paper-based device. Okay. The problem with colorimetric detection is that the detection limits are very high. That is, you may be able to detect only parts per million. You may not be able to detect parts per billion, which may be the concentration levels present in the wastewater stream. So how do you overcome this? So again, we use a very simple idea from chemical engineering, which is we try to pre-concentrate the solution by adsorption. Okay? So that's basically what we're trying to do here. We're trying to show that you take a solution with a very low concentration of heavy metals, you add some adsorbent, could be some clay, kaolin or something. The chromium ion, metal ion for example, gets adsorbed on the clay particle. So it gets concentrated on the clay particle from the aqueous solution. You filter this. When you filter it, so you have the chromium ion on the solid adsorbent, and you do the colorimetric assay on the solid in the solid phase on the kaolin. So basically, we are having a pre-concentration step through this adsorption. Okay, what the adsorption does is it basically does the concentration. So although you may have ppb level in the solution, the concentration, the adsorption has increased the concentration level, and you get a color change, and you are able to make a measurement. Okay, and you can correlate the aqueous concentration to the color intensity. So that's again chemical engineering principles being used to address this problem. Okay. I think so this is basically a table trying to tell you that if you have adsorptive colorimetry, you can actually go down to a very, very low level of detection compared to the spectroscopic measurement and the non-colorimetric and non-adsorptive measurement. Okay, I think I'm just have a couple of more examples and we'll stop. We have this application is for the detection of cervical cancer. This is a common problem in women, and we want to develop. So, if you want to do a test, a screening test in some remote village, you want to again make a device. Okay. So, this here we tried many colorimetric tests, many things, many dyes, and finally we came up with. So, I'm just telling you the thing which worked. There are many things which we tried which did not work. Okay, so I'm not going to bore you with all of that. So finally, what worked is do it in a modular manner. You would exploit the fact that you can do this modular, because each of these microfluidic reactors is going to be one module, and I'll have 1,000, maybe millions of these modules, and that's how I would try to meet the demand of caustic soda. Okay, so that's where microfluidics comes in. There are two advantages which I didn't actually stress. One is the fact that supposing you have very exothermic reactions, then the surface effects are so large that any heat which is generated can be easily dissipated. So you can actually carry out exothermic reactions in a very safe way in a millireactor or a microreactor. Whereas if you were to do it in a large scale reactor, you would have a problem of possibly a safety hazard, an explosion or something happening, a runaway reaction happening. So there are some examples, if you are dealing with hazardous chemicals, for example, if you have to synthesize something or maybe a pharma product which doesn't necessarily need large volumes, then that can be done in the briefcase. So I was just trying to show you how you could possibly think in terms of briefcase. Briefcase may not be possible for caustic soda because you can't carry that with you, but there may be some places where you need some hydrogen or something generated at a local point for doing some reaction or some characterization, whatever it is. Then you can think in terms of briefcase. So I was just trying to explain to you the different possibilities of how microfluidics can be used. So one is briefcase, one is modular, then sensors. So all these are where microfluidics can fit in. Yeah. Anything else?
See, otherwise scaling up is not a problem with microfluidics.
It is numbering up. We call it numbering up. We just have a lot of these modules in parallel. In chemical engineering, when we talk about scale up, we talk about having a small reactor and going to a much larger reactor. So there we have to be very careful because the volumetric effects are scaling as characteristic length Q. Surface area effects or heat transfer scale up as characteristic length squared. So those things have to be factored in. Here we just do one design and then we just replicate it, duplicate it. Yeah.
So what is the size distribution of the nanoparticles you prepared with this ATPs?
The size distribution?
Yeah, size.
So, depending on the conditions, we have been able to go from 5 to 10 nanometers. That's the distribution we have.
And what the distribution? That is the mean size what you are.
No, I'm talking about the distribution from 5 to 10. The distribution is from 5 to 10. So, mean would be somewhere in between.
If we go with single phase flow, we are not taking two phase flow. What are the advantages and disadvantages for the mini channels?
Single phase flow, the problem is mainly that you have axial dispersion effects, and so the size distribution which you get is very broad because the liquid in the middle is going to flow at a much faster rate. Okay, so what you have to do is that is spending less time, so you will get a different size in the middle, whereas in the walls it's spending a longer time. So you will get a different size particle. So because of the parabolic nature of the velocity field, you would get different kinds of particle sizes because the time spent by different fluid elements in the cross section is different. You overcome that by trying to make the channel curve and bringing the mixing in the radial direction, trying to make it more homogeneous. The advantage, of course, what happens is in a microfluidic channel, the transport is mainly going to occur by molecular diffusion. And molecular diffusion is a very slow process. Okay, so you want to try to accelerate the molecular diffusion. Of course, the distance through which it has to travel is very low. That's an advantage. But still, your diffusion coefficients are of the order of 10 power minus 8. Okay, and your channel is about 10 power minus 3. So you need to still wait a lot of time for the diffusion to homogenize things. And the reaction is already occurring.
Actually, I have tried with helical tubes for copper nanoparticles. I got around 2 to 5 nanometer size, and the issue is very narrow.
Yeah. And that's
what you say good that with the armature and
yeah. That usually in single phase, that's what we would do.
Right.
So, okay. Anything else? So, yeah.
I think you finish it.
I will. I have a couple of more slides. That's all. I think I will not. Thank you for being so patient. Okay. So, cervical cancer is something we want to detect, and what we found is that Pico green is a dye which can help differentiate between positive patients and negative patients. So we went through a whole bunch of dyes, and this basically works on the principle of fluorescence. So earlier was colorimetry, some biotechnology. This is basically fluorescence imaging we are doing. So we take the sample, we go through a bunch of steps. Okay, we take the DNA, we amplify it, and I will not bore you with biotechnology, but you will add the dye Pico green, and you see the difference between the positive sample and the negative sample on the right lower corner. So the difference in the image. So we basically have made a small device which you see here, okay, which can help. So you have light of a particular wavelength passing because through a filter. Because of the fluorescence, you have another filter. You take the image of the higher wavelength and then do the image processing. And you can clearly see the difference between the negative and the positive samples. So this is one way by which you can distinguish between a patient who has cervical cancer and who doesn't have. So,
sorry to bother, can you highlight the difference, because frankly I'm not able to make out the difference.
You're not able to see, there is a fluorescent ring in the positive sample on the right hand side. Okay, I think that it is shadow. So here, but you get a nice fluorescent ring here. There is an angular ring which is fluorescent. You don't have that here. Okay. The negative sample is more uniform. So the positive sample has a fluorescent ring, whereas the negative doesn't. Okay. I do not know.
You visually detect that, or
you can. You have to take the image and then you can do the image processing. Yeah. You can also do visual. You can also, so we scan and then do the image processing. You can also do visual. And in fact, my student took out the sample of over 8 months and it's still having that fluorescent ring. So it's quite stable, this device. Okay. Okay. Last example, and just to give you an idea about how it can be used in agriculture. Neem seed is something which we are all used to, and it has a lot of nice properties. And in the neem seed, you have a particular chemical called azadirachtin. And that's the one which imparts all the properties. So the price of neem, the quality of the neem seed is decided by the percentage of azadirachtin which is present. And one way to do this analysis is through again some colorimetric change. But the problem is this uses concentrated sulfuric acid. Now I was talking earlier, when you're talking using hazardous chemicals, we're talking using low volumes. That's a nice thing. You are using a microliter of concentrated sulfuric acid. But then not all paper substrates will withstand concentrated sulfuric acid. Only some paper substrate will withstand concentrated sulfuric acid. So that's something which we had a challenge with. So my student went and they did a whole bunch of tests, and they finally found one. So many of the paper substrates actually burned, and only one particular substrate. And there are other features that you want. You want it to basically be hydrophilic, the paper. So we finally found that the glass microfiber filter paper was the best. So my point is, you will have challenges. The point I'm trying to make here is there are challenges. Okay. In the cervical cancer detection, which dye would work? That was a challenge. In this, which paper would work is a challenge. So there are challenges, and you need to understand what is the thing which is causing a problem, so then you can overcome the challenge and find a solution. I think that's the message, broad message, which I'm trying to tell you. Okay. Finally, I hope what I've done, this is my last slide, is that your fundamentals are very important. Okay? And you need to have very strong fundamentals if you are going to do any work, be it make a sensor, be it trying to reduce the size of a chemical plant, whatever it is, mixing, colorimetry, fluorescence, whatever it is. It is always good to do things in your lab. So in a lab, your sensor works beautifully. So and this is a common tendency we have in the lab, because you are doing everything under a very controlled conditions, right? you are using, making a sensor for chromium, you have only chromium and then it is working. But when you go into the real field, you will see that the other compounds are also present. So you need to do extensive testing. Okay? And what we need to do is, and that's a different kind of a mindset. So we do a lot of good work in the lab. I'm sure there's a lot of good work being done in the labs here, but to take it to the field, okay, is something which needs a different mindset. Talking to industry, see the challenge, do a lot of testing, get it to work, get a commercial product, okay, out there, with having a tie-up with an industry, getting a product in the market. That's a different ball game. So you need students with different mindsets to work. One who's interested in taking it to the market, one who's interested in deep science, and things like that. And if that network is built, I think most of the challenges which you are going to face, I've taken microfluidics as an example, but you can do this in any field. Whatever I'm saying is very general. It's going to be something which is very important for a team to work looking at different aspects to make a commercial product. Okay? So with all this emphasis on innovation and all that, we are happy about all these papers we published. We've filed a lot of patents, but unless you get a product and somebody buys my sensor by giving me 1 rupee, it's not worth it. So we have to do that. Okay, thank you very much for your time.
It's already we have interacted, but if there are some more questions, we can engage with the speaker now. Yes,
Most of these examples are liquid phase reactions. But what about gaseous phase reactions? Because at the micro level, there are many challenges in gaseous phase.
Yeah. So we have focused mainly on liquid phase reactions. You are right. Gas phase reactions, of course, the diffusivities are much faster. Okay, and but there are sensors in the market for detecting gas phase pollutants also. So we can also extend these ideas, but there are different challenges, and you have to overcome them. Yes.
My question is from that cervical cancer device. So actually for that we need to amplify the DNA of CD. So for amplification of DNA we need a big machine. So those are very expensive, but can we design such a microfluidic device that would DNA amplification is at the room temperature inside the microfluidic channel?
I think it's a very good question. It's a very specific question. Very good. So right now, what we do is we have done the amplification using lamp. Okay, at 90 degrees Celsius, we do the amplification in the liquid phase, and then we take the amplified DNA and then do the detection in the paper. Okay, right now this question is, you need an amplification of the cervical cancer cell DNA to do the detection. That's absolutely correct. So now to do the what we have done so far is, what I've showed you is amplification in the liquid phase, but we don't need an expensive device. Okay, you can just use a regular PCR machine, regular machines. What we are now doing is coming up with a method by which we can do the amplification also on paper. So we want to do the amplification on paper, and with the small heating step. What you are saying is correct. You need a small heating step for doing the amplification, because you need to take the cell and then release the products. So we need to do that. So we are integrating the entire thing on paper, the amplification and the detection through a sequence of steps on paper.
Can I add to that? Recent work with IGIP group. Someone who was identifying the coronavirus on the paper. And they also mitigated or bypassed this PCR requirement and doing amplification of coronavirus on paper and detection of paper. So Feluda.
Yeah.
So Dr. Suman.
Yes. Yes.
Named it after the Bengali detective.
Yes. Yes. Yes.
Any other questions? Yes.
You talk about microfluidic reactor, as you said, and you propose a design as a relaxed but because in microfluidic reactor velocity is also limited, so how much flexibility can we get with relaxing?
get very good mixing with microfluidics in the centrifugal action. So what I was talking about is basically what is called a passive mixer. That is, you are just changing the geometry and then you are trying to get the mixing by getting the centrifugal forces. Okay. So if you saw the helical coil reactor that I had on a rectangle, what we are doing is we change the direction of the coil through every 90-degree bend, and that really improves mixing a lot. So the mixing depends upon the curvature, which means the radius of the tube and the radius of the circle over which the thing is bending. So you can, there are some parameters which you can control to improve the mixing. Okay, so you could get very good mixing, even though the velocity is low. Correct. And you have to understand that the dimensions of the reactor are also very small. So the distance over which the mixing has to happen is also very small. So you're talking about 200 microns distance over which the mixing has to take place. You're not talking about mixing over a very large length scale. So that is also an advantage.
So,
Yeah.
so in paper-based we started that will be back to
Yeah, so you have to make sure so this question is, you have a reagent at one end and then you add the analyte at the other end. So you have to optimize the volume which you are adding to make sure that the reagent is located only at the end that you want. Okay. So when you make your design, so there's a protocol which you have to come up with. How much volume? Is it 2 microliters? Is it 6 microliters? So you do a battery of tests to optimize what is the volume which has to be added.
second
I would not say it is hit and try. It's a systematic way to find out. Okay, I do a lot of modeling. Okay, so you can actually calculate what is going to be the volume which you add, which can be retained in that circular drop. So if you don't want to do modeling, you want to blindly do only experiments, then it's hit and trial. But if you want to do modeling, then it's not hit and trial. It's a very scientific way. You put a drop, talk to Dinesh, he does a lot of modeling. He will put a drop and you will try to find out whether the drop is going to spread or not. But again, you have to use conservation of mass, conservation of energy, momentum to understand the flow.
You were talking about when you were talking about like you're making those nanoparticles. Each and every time that you are adding the two different fluids, but the part like the droplet size will remain same. So is that depends on the inlet velocities that you are giving, those are same, or you can vary those velocity ratios depending on that?
So the size of the droplet definitely depends upon the flow rates of the two liquids, the aqueous phase and the organic phase. So by controlling the flow rates of the two liquids, you can control the size. Okay? That's one thing we normally do, one way to control. And of course, you can also go from droplet size to parallel flow if you change the flow rates too much. Okay, so that's something. So there are flow studies done separately. Then you realize that this is the region where I have to operate to get my two-phase flow, and then in that region you are operating.
So usually, when you are making it safe, both the velocities are same. After what I'm saying, that can we get a distribution of different size of droplet if you change the flow rate in such a way?
When you talk about okay, so the answer is yes. Okay, the answer is yes, but you may not be able to control it. For example, what happens is if you have an aqueous two-phase system, you have two different solutes. Okay, and when there is mass transfer going on from one phase to another, because normally you are talking about mass transfer from one phase to another, you could have surface tension gradients which are going to be occurring. Okay, because of the surface tension will keep changing along the reactor, and that can give rise to a change in the size of the drops.
Do we get Marangoni instability across those?
You will get Marangoni flow. I will not call it instability. I will get.
At times that you are getting stable drop.
Yeah. I will get Marangoni flow, which has to be possibly included in describing the flow field, not just the shear stress. Yeah. So, because you have mass transfer from one phase to another, you will also have other effects which can change the properties of the liquids. So those things can give rise to a change in the drop size as you go along the reactor. Okay.
Downstairs. One thing is, like, just for curiosity, like, is this paper strip microfluidics that you are talking about? So how many times we can use it? Like all those.
One time.
One time.
The paper strip is disposable. You don't want disposable.
And those disposable things are those safe, like in the environment, like when we are doing or we are.
No, I mean, to be very honest, we are not focusing on the safety aspects right now. We are only making sure that the thing works. Because we are using all kinds of dyes and chemicals. Okay, the paper strips are going to be, if I say safe, he's going to object, he's from chemistry department, so I'm not going to say they're safe. But I think there are lots of chemicals that are used, and these are definitely not easy to dispose. But the advantage is you are dealing with microliters of chemicals. Okay, you're not dealing with large volumes of chemicals. That's the advantage. Yeah.
Perhaps the last question.
So you were talking about modeling and checking the amount of fluid that is required to put the drop in particular place. So sir, we were facing a kind of challenge in modeling the flow on a paper channel or a cellulosic channel. So what kind of surface or model can be used in that regard?
Can you tell me you're modeling what?
So actually when we need to put a drop on the paper channel and then it flows, so when we need to model it on console or anything, then we are facing a challenge of selecting a particular surface. What kind of surface do we choose?
Okay, what kind of
meshing needs to be done?
Okay, surface. Okay. So I normally do first principles modeling, which means I basically write down the conservation equations, etc., and then I do the modeling. Of course, these days lots of packages are there. So when you talk about COMSOL, I'm pretty sure it's quite powerful and you can do it. But we have not really used COMSOL for our simulations. So what we do is we use Darcy's law, for example, for the flow through the porous medium. Okay, and there is something called the Washburn equation. So these are basically, you may be aware of this. So which talks about flow through porous medium. So this is basically what we use, and we look at the specific, and you need to be very clear about the physical properties, things like contact angle, what is the surface tension, okay, to include it in the model in a proper way. The problem when it comes to all these commercial packages, I mean, you have to handle it properly. So since to me it's a black box, I normally don't do it. I like to write my own model because I think I have a better grip of the equations and try to get solutions which I can interpret and get physical insight from. So what we normally do is write the conservation of mass equation for the drop and look at the flow of the drop, how it's penetrating the paper substrate, and then in the paper substrate we look at Darcy's law to understand the flow. Okay. And depending on the geometry, whether it's a radial geometry or a rectangular geometry, we use the appropriate equations. But if you have specific questions, I'd be happy to send me an email. I'll be happy to answer. Okay? Yeah.
So, sir, very nice presentation. But this paper-based devices, most of the time these are indicatives. The numbers which we get is very random sometimes and may not be very accurate. Like blood sugar monitoring, which we do, can be many numbers, and that may not be correct. But indication is fine that your sugar is going up or coming down. But if I go with actual number and do it with the pathology or traditional way matching, the numbers are very different. What is the reason behind this?
Okay. See, when you design your sensor, I mean the paper-based sensor, the flow has to be uniform. Okay. So the idea is, if your flow is not uniform, then you could have a problem. I mean, you think that all the reagents that you added a certain microliters of this, and if your paper-based strip is, for example, not properly made, not properly fabricated, you will get an error. See, it is necessary that the wax in the hydrophobic region penetrates the paper fully so that there is no flow underneath the paper. So, you just coat the surface of the paper and then try to do the test. Maybe the liquid you're adding is not going to go to your reaction zone, but it is going underneath the paper and then it doesn't reach. So that could be a source of error. This is one possible example. So you need to make sure that you would take all the possible precautions to make sure. Then that will only come by repeated tests. Any device, I mean, you need to do millions and millions of tests to get confidence. So, I mean, you can do the calibration and all that, but if you think, okay, it worked once, so I got a calibration curve, second time you may not get it. So you need to make sure that, and when you do it, you'll get a good result. If he does it, he doesn't get a good result, then there's a problem. It can't be dependent upon the person. So these, non-homogenities have to be factored into account.
So I was mentioning like the sugar machine, which is available in bulk, and I think many companies are making. Still, the accuracy is not there. If I take 2 sugar machines, and I have tested that with my mother, that we took 2 sugar machines, we tested it, and the difference was around 40.
Okay.
So that is a very big number. As per one, it was very high sugar. As per one, it was fine. It just above the limit. So this becomes a very dangerous solution. Once we try to commercialize it, that some people can get panicked that my sugar has crossed to 50.
I understand. I understand what you're saying. So it may have to do, because what you say is just put a drop of blood, and the drop of blood is a very qualitative term. You don't specify the milliliters or microliters that you're adding. So this could be a problem.
So how to overcome is that if you are doing the mass manufacturing, because this is finally for public application.
I think this is a problem, and I think Siddharth Panda of Kanpur, he has been talking about this problem in several places. That this is a problem. So you want to try and make devices which are more specific, more sensitive, that kind of a thing. The assured criterion that I spoke about, some of those criteria may not be met. So, I think that's a very important problem that we have. Okay?
Sure, there may be more questions, and I'll be happy to take questions. I now request Dr. Dinesh, who was instrumental in getting Pushpavanam here, to come on the stage and felicitate the speaker and give him a small token of Thank you very much, Professor Pushpavanam, for sparing your time and having interacted with us and given us some introduction about microfluidics and its possible applications. I'm sure students would have taken a few from it, and if interested can pursue on this line further. I thank you all for your patient listening.